Hi everyone, my name is Yichi. I'm a second-year PhD student in the Computer Systems Lab at Cornell. Today, I'm going to introduce precision gating, improving neural network efficiency with dynamic dual precision activations. This is a joint work between me, Yichi Zhang, Weizhe Hua, Nayun Xu, and advised by Professor Edward Sa and Professor Zhang. Quantization is a promising way of reducing the compute cost of neural networks. Even for a highly compact model such as ShuffleNet v2 for ImageNet, we can quantize it from floating point to 8 bits while preserving the prediction accuracy. We use the blue circle to represent the fixed precision. The smaller the size of the circle, the lower the bit width. If we quantize the model aggressively to 6 bits or even 5 bits, we can save more compute cost. But meanwhile, there will be a non-trivial accuracy degradation. We notice that for a given input, certain features contribute more to the classification results. So we ask this question: can we compute most features in low precision and dynamically figure out important features for each input and compute them in high precision to preserve accuracy? Explicitly, we can split the full precision activations, say 8 bits, to 4 most significant bits, represented by a top half blue circle, and 4 least significant bits, represented by a bottom half blue circle. We can first approximate the output features using the MSB activations. Then we use a threshold delta to gate the partial output features to predict which ones are important to the given input. We only update these important features to full precision by using the head mount product. Ideally, most features will be computed using low precision. The importance of the features is input dependent, so it is dynamically predicted during inference. Here's an example of showing how precision gating works on a convolutional layer. We split the input activations again into MSBs and the remaining LSBs. First, in the prediction phase, we use the MSB activations to generate a partial sum. The partial sum represents the importance of the output features. We then use threshold delta to gate the partial sum to predict important features. This generates a binary Musk tensor. Note that each channel in each layer has its own gating threshold delta to make it a fine-grained gating. In the update phase, we do a sparse update using the Musk and increase the precision of those important output features. And finally, we combine the results from both paths and generate the output features. The good thing is the gating thresholds are trainable, so they learn to adjust themselves to the activation distribution. Also, this method works for different activation functions such as sigmoid and tanh, not only for ReLU. Interestingly, we can exploit the sparsity in both forward and backward propagation. First, we define the prediction phase as a convolution between weights and MSB activations. We define the update phase as a convolution between weights and LSB activations. Note that the weights are the same in both phases. The Musk is a binary tensor. We only have a 1 when the partial sum in the prediction phase is larger than the threshold. The forward path can therefore be returned as the prediction phase combined with some sampled compute in the update phase. Here, we square the Musk element-wise in the update phase. Given that Musk is a binary tensor, the element-wise square operation preserves the same value. However, after the modification, an additional Musk term is introduced in the backward propagation in computing the gradient of O with respect to the gating threshold delta. We find in this way, sampled dense compute kernels are in both forward and backward paths, as shown in the red circles. This helps accelerating both training and inference. Moreover, the gradient to delta now only requires a sampled compute of the update phase, which has already been computed in the forward pass. Here, we show the results of precision gating. BHB is the number of bits we use in the prediction phase, and B is the full precision bit width. B average is the average bit width. It reflects the compute cost. On CIFAR-10, we find that precision gating is at most 17% more accurate than the prior work, and it improves the compute efficiency by up to 3.3x. Surprisingly, precision gating is computing mostly under 2 bits on CIFAR-10. We also tested our method on ShuffleNet, ImageNet, and LSTM PTB. We observed the same trend that precision gating dramatically improves the compute efficiency while preserving the model accuracy. They are both able to compute mostly under very low bit width. Conclusively, precision gating improves the accuracy efficiency trade-off. It not only works for the convolutional neural networks, but also works for recurrent neural networks. Thanks for listening. Our work is open source on GitHub. Feel free to check it out.